Batch processing handles fault tolerance elegantly. If a MapReduce task fails, the framework discards its output and reruns it from scratch. The input is still there on HDFS, unchanged. The failed run leaves no trace. The rerun produces the same output as the original would have. Batch processing is naturally idempotent at the task level. Stream processing has no such luxury. Events flow in, transformations execute, and results are written to output systems, databases, search indexes, email queues, notification services. If a task fails and is rerun, those external effects may have already happened. The database write may have already occurred. The email may have already been sent. You cannot unsend an email. This is why exactly once semantics, the guarantee that each input event is processed exactly once, producing exactly one output, even in the presence of failures, is the hardest guarantee in stream processing. There are 3 tiers of delivery guarantees. At most once means, process events and don't retry on failure. Events may be lost. Simple to implement. If it fails, move on. Suitable for best effort metrics where occasional dropped data points are acceptable. At least once means, retry on failure, which means events may be processed more than once. The output system sees duplicates. If your output is a sum counter, the counter will be incremented too many times. Suitable for idempotent operations, ones where a duplicate application has no additional effect. Exactly once means, every input event is processed precisely once even if tasks fail and are retried. No lost events. No duplicates. This is what financial systems require. It's what any system producing accurate aggregates requires. And it's what stream processing frameworks have been racing to achieve since their inception. The 2 main approaches are microbatching and checkpointing, and they make opposite trade-offs. Spark Streaming's approach to fault tolerance is conceptually simple: don't build a streaming system at all. Build a fast batch processing system that runs tiny batches. Spark Streaming divides the input stream into small batches, by default, every 500 milliseconds. Each batch is processed as a complete mini MapReduce job. If a batch fails, it's rerun from scratch exactly like a normal Spark batch job. The input data is buffered in memory until the batch is complete and its results are committed. The result is exactly once semantics with the same mechanism that makes batch processing naturally fault tolerant. The input is always available for replay. The batch either succeeds and produces committed output, or it fails and is rerun. There are no partial outputs. The cost, latency is bounded by the batch interval. You cannot achieve sub-second latency with 500 milliseconds batches. You're also introducing artificial synchronization points every 500 milliseconds. True streaming, processing each event as it arrives with single event latency, is not achievable with microbatching. Apache Flink takes a fundamentally different approach, the Chandy-Lamport distributed snapshot algorithm, adapted to stream processing. Flink periodically injects checkpoint barriers into the stream, special markers that flow through the operator DAG along with data. When an operator receives a barrier on all its inputs, it snapshots its state to durable storage and passes the barrier downstream. When the final output sync acknowledges the barrier, the entire checkpoint is complete. On failure, Flink restarts from the last complete checkpoint. All operators reload their state from that snapshot. The stream is replayed from the source, Kafka, which durably retains events, from the offset corresponding to the checkpoint. Processing resumes exactly where it left off. Flink achieves true record at-a-time processing with sub-100 ms latency and exactly once semantics. The trade-off, checkpoint overhead, and the source must support replaying from an arbitrary offset, which is exactly what Kafka provides. Microbatching and checkpointing ensure the stream processor sees each event exactly once internally. But the output side introduces a new problem. A stream processor can fail after processing an event but before confirming the output was committed. On restart, it reprocesses the event and writes the output again. The processor had exactly once semantics, the output system saw the write twice. The book solution, make output writes idempotent. An idempotent operation can be applied multiple times and always produces the same result as if it were applied once. Setting a value is idempotent. Setting a key in a key value store to the same value twice results in the same state as doing it once. Incrementing a counter is not idempotent, doing it twice increments by 2. Adding a record to an append-only log is not idempotent unless you deduplicate. Kafka Streams and Flink both implement idempotent writes to Kafka by assigning each producer a unique producer ID and sequence number to each message. The Kafka broker rejects any message whose sequence number is not exactly one more than the previous message from that producer, detecting and dropping duplicates. This idempotent producer was introduced in Kafka 0.11, 2017. For cross-system exactly once, ensuring that a write to Kafka and a write to an external database both happen exactly once in the same operation, Kafka introduced transactions in 0.11 as well. A stream processing application can read from one Kafka topic, write to another Kafka topic, and commit its consumer offsets, all in a single atomic transaction. Either all three succeed or all three are rolled back. This transactional approach only covers the Kafka to Kafka path. Writes to external systems like Elasticsearch, Cassandra, or PostgreSQL still require those systems to support idempotent writes or duplicate detection. The combination of Flink checkpointing for internal state plus Kafka transactions for output provides the strongest end-to-end exactly once guarantee available today in production stream processing systems.